Hello. In this video, we're going to begin to study radicals, which are going to be part of our next unit. But to do so, I want to do a bit of a warm-up question here. So we have some blanks here, all underneath roots, and we want to consider the numbers 1 through 9. And we want to put the numbers 1 through 9. If you notice, there's 1, 2, 3, 4, 5, 6, 7, 8, 9. There's 9 blanks, so use the numbers 1 to 9 once and only once. And we want to do it in such a way that each one of these roots turns out to be a whole number. Now for the first one here, you could think, oh, maybe I'll put like a 4 in there, because square root of 4 is 2. For the second one, we have two numbers. They're going to be like a 2-digit number, so like maybe 25. Square root of 25 is 5. Here we're going to add the numbers. Here you're going to have one number under a root, and then add, and then this is going to be some number root. Like the second root is the square root, but the third root is the cube root, and so on. So if you go ahead and give that a try, pause the video and see if you can come up with a way of putting all the numbers in. All right, so assuming you gave that a try, here's one solution that you could do. You could have a 4 there. Then you could have a 16 here. 2 plus 7 will be 9, so that'll work out. Here we need another number that just goes underneath the root, so that's probably a 9 there. And then you can throw any number over here because it's a whole number already. And then I like doing the third root, the cube root of 8. So there you go, we got the numbers 1 through 9. This is 2, this is 4, this is 3, this is 3 plus 5 is 8, and this is 2. They're all whole numbers, they all check out. Now there's more than one way to do this, so if you found a different solution, by all means, just check it and make sure they all evaluate to whole numbers. But this is a good practice for seeing what gives you a whole number and what doesn't when you square root. Now, speaking of numbers that don't square root nicely, what's the square root of 11? Well, I mean, it doesn't work nicely, right? We know the square root of 9, that's going to be 3. We know the square root of 16, that's going to be 4. But the square root of 11, it's kind of sandwiched in the middle somewhere. So it's not going to be a whole number, but in fact, the fact that we can show it's between these two roots is really useful because it means that even though it's not a whole number, it's somewhere between 3 and 4. And if you notice, 11 is a little bit closer to 9 than it is to 16. So it's probably going to be a little bit closer to 3, maybe like 3.2 or 3.3. And we can get an approximation. An approximation for the square root of 11. This is sometimes called doing your benchmarks. These two numbers here on either side of 11 are the two perfect squares on either side. And they allow you to benchmark the square root of 11 somewhere between 3 and 4, probably closer to 3 than to 4. Now, if you grab your calculator and just check, it's actually 3.317. So yeah, 3.3 is a pretty good approximation. Now for something like square root 12, again, we could benchmark it. It's going to be a little bit more than root 11. So maybe we could say square root of 12 is like maybe 3.4 or something. But we also can simplify square root 12 because the number 12 can be written as 4 times 3. Now there's other ways to write 12, right? It's 6 times 2 or 12 times 1. But we want to pick the one that has a perfect square in it. We want to write 12 as a perfect square times some other number. Because then we can use this rule. If you have two numbers that are multiplied together, you can just square root each one and then keep on multiplying. And because 4 is a perfect square, we can write this as 2 root 3. So the number 12 simplifies to 2 square root 3. And you might say, well, why do we want to simplify it? Well, the square root of 12 is quite large underneath the root. Now we only have the 3 underneath the root. So we've gotten rid of some of what's underneath the root. That's one way of thinking about it. Another is we might be able to simplify things. We might be able to combine. We might be able to determine something in its simplified form that we couldn't in its more complicated form. And here's just such a question. We have the following radicals, 1, 2, 3, 4, 5 of them, and we want to order them from least to greatest. Now, they're all over the place. I mean, this one looks pretty big, but also this one has like a 6 in front of it. And it's hard to tell really which one is which. I mean, I know this one is bigger than this one, But this one's got a 5 in front, so does that make it bigger than this one or not? It's hard to sort of compare them the way they are. So what I would encourage you to do is pause the video and simplify each one of these radicals. Because when you do, you're going to find that they're a lot easier to compare. So go ahead and pause the video and give that a try. All right, so assuming you gave that a try, here let's do this first one. So we have 6 root 12. So it's 6 times square root 12. We could write that as 6 times root 4 times 3, 6 times 2 times root 3, so 12 root 3. Okay, let's do the same thing with this one. Now 675, there's definitely going to be a 25 in there. So we could think of this as, well, I mean, there's lots of ways to do this, but we have to break the number down and see what kind of perfect squares we can get out of it. So 675, if we started with just dividing by a 5, we'd have 5 and 135, kind of making a little prime factor tree. We could divide the 135 by 5 to get 5 and 27. 27 divides by 3, so we'll get 3 and 9. And 9 is 3 and 3. So here we would have 3 times the square root of 3 times 3 times 3 times 5 times 5. And what we want to do is group each one of those pairs. So you'll put 2 3s under a root, you'll put 2 5s under a root, and then you put that last 3 under a root. Now the square root of 3 times 3 is just 3. The square root of 5 times 5 is just 5. But the last 3 is kind of left all alone under the root. So unfortunately that guy doesn't get to pair up. So this simplifies to 45 root 3. Now if we look at these two, we could say, oh, well yeah, 12 root 3 is less than 45 root 3. If you have 12 apples or 45 apples, right, which one is less? Clearly the 12 apples. Even though I don't know the exact value of square root 3, because they're both in terms of root 3, I know that the 12 is going to be smaller. Now we go ahead and continue doing the same thing for each one of these radicals. So over here, this one is going to become 30 root 3. That's because the 108 can be divided by a lot of 2's, and we can pull out enough to get a 30 root 3. When we go to the next one here, square root of 1323, that's going to become 21 root 3. And finally, the last one here, square root of 19200, that's going to be 80 root 3. So if we're going to finally write them in order from smallest to largest, it looks like we would have 6 root 12 is the smallest, or we could write it, maybe I'll write it in the simplified form. It's kind of nicer that way. So we have 12 root 3, then 21 root 3, then 30 root 3, then 45 root 3, and then finally 80 root 3. All right, here's another question involving radicals. What's the smallest positive integer x such that 1050x will be a whole number? So this is a bit of a puzzle here. Go ahead and pause the video and see what you come up with. All right, now some of you might be saying, oh, Mr. Peters, I got this. If I have a number and I multiply it by the same number, then obviously when I square root it, I will get a whole number. And I would say, well, yes, x could definitely be equal to 1050. That would be an integer that would give you a whole number there. Or you might be thinking, well, what if I just multiplied it by 0? Okay, the square root of 0 is a whole number, so maybe that works out. And I would say, well, okay, that didn't quite follow the instructions. It needs to be a positive integer. This is not allowed. But maybe this is the right answer, the 1050. But we're actually looking for the smallest x. Is there an x smaller that will still give you a whole number? And the way you might approach a question like this is you start with the 1050 and you break it down. Now, 1050, we could divide by 10 because it ends in a 0. And then we could divide the 10 into 2 and 5. Here we could divide by 5, so that'll be 5 and 21, 3 and 7. Now, if we were to write this underneath the root, we could group the two 5s together. But if you notice, the 2 and the 3 and the 7, they're all left under the root. Really, if we try to simplify this radical, we end up with 5 root 2 times 3 times 7, or 2 times 3 times 7, which is 42. And because the 2 doesn't have a partner, and the 3 doesn't have a partner, the 7 doesn't have a partner, they can't come out of the root. So what we want to do is underneath the root, we want to add a 2 and a 3 and a 7. That's going to be our x. Because now the 2 partners up and it comes out. The 3 partners out and it comes out. The 7 partners up and everything comes out of the root. So our final whole number, if you want, is 5 times 2 times 3 times 7, which is 210. And our x is 42. Now, if that was a lot of work, we can go back and check that. 1050 times 42. If you type that in on your calculator, the square root of 1050 times 42 is going to give you the square root of 44100, which is exactly 210. So we get a whole number in the end, and the smallest x value that works out for that is 42. All right, a couple more things with radicals as we're reviewing. Let's say we had square root 12 plus square root 48 plus square root 3. Right now we can't add those because they're all different roots. But if we do that simplifying style, we can write this as 4 times root 3. We can think about the 48 as 16 times 3. And then the root 3 will just leave as a root 3. So the 4 comes out to give you 2 root 3. The 16 comes out to give you 4 root 3. And then you have a root 3 at the end. And now it's like you have 2x plus 4x plus x. That's just going to give you a total of 7x, or 7 root 3. So we're actually able, if we simplify our radicals, to sometimes combine them, and again, to get a simpler version. So let's put this all together on a super problem. Let's say you had the square root of root 720 plus 4 root 80 divided by 2 root 20 plus root 500. So pause the video and give this a try. I guarantee you that this whole thing simplifies to a nice, beautiful, very small radical in the end. But if you're going to get it, you have to be very careful and simplify each radical as much as possible. So pause the video and give it a try. All right, so let's start with that root 720. So 720, well, we can divide by 10. So that's going to give us 72. So 10 and 72. Then we can take the 72 and divide that by 2. That'll give you 36. We could do that as 6 and 6, and the 10 is 2 and 5. So that means root 720, we have 2 2's, we have a 5, and we have 2 6's. So the 2's come out, the 6's come out, giving you 12 in front and 5 underneath. All right, let's try, so it was right here. Let's try the 4 root 80. So 80 is going to be 10 and 8. 8 is 2 and 2 and 2, if you want to break it up 3 times. 10 is 2 and 5. So 4 root 80 is 4 times, well, there's a couple of 2's and a couple more 2's, and then a 5. So 2 2's come out, and 2 2's stay in. So that's going to give you 4 times 2 root 5, or 16 root 5. All right, so if we add these two together, we have 2 root 5 plus 16 root 5, and that's going to give us 18 root 5. So the numerator underneath the big root is going to give you 18 root 5. Let's keep going. We got 2 root 20. That's going to be 2 root 4 times 5. So that's 4 root 5. Then we've got the 500. We could write that as root 100 times 5. Square root of 100 is 10. Now we got to add these things together, and that's going to give us 14 root 5. Oh, just back up one sec here. I think I missed the 12. I put 2 root 5. That should be, 12 root 5 plus 16 root 5. So that will be 28 root 5. Okay, so we have 28 root 5 on the top and 14 root 5 on the bottom. So let's put these together into our final question. Square root of 28 root 5 over 14 root 5. The root 5's cancel. And 28 over 14 is just going to be 2. So our final answer is the square root of 2. Hooray! The giant radical simplified all the way to just give me the square root of 2. All right, let's go ahead and take some notes on this. The basic idea here is we are working with radicals. Working with radicals. And so there are a bunch of different skills that we needed to review. There was the idea of a benchmark. So that's where you have root 11, which is between root 9 and root 16. In other words, it's between 3 and 4. In other words, we're going to approximate it as 3.3, approximately. We have the idea of simplifying. So if you have root 12, that's root 4 times 3, which is 2 root 3. And we even have the idea of like terms. So if you have 2 root 3 plus 5 root 3, you get 7 root 3. This is like terms. So these are all skills that hopefully you've learned with radicals before, but we're nice and reviewing them all together now, just so we've got it all in one quick lesson. So as an example, let's try to simplify the square root of 1152. So see if you can simplify that. All right, assuming you gave it a try, it's nice to work on those prime factor trees. That's kind of the best approach here. Divide by a 2 and you get 576. Divide by another 2 and you get 288. Well, they keep being divisible by 2 because they end in an even number. So, you know, if it ain't broke, don't fix it. Keep dividing by 2s. Okay, I'm running out of room here. Let's put this 72 over here. So 72 is 2 and 36. And that's going to be a 6 and a 6. We can grab that perfect square there. So we got a 2, 2, 2, 2, 2, 6, and 6. You don't have to wait until they're all primes. If you find two numbers like a 6 and a 6, you could break them down as 2 and 3, 2 and 3, but you could also just leave them as 6s. So this is going to be 1, 2, 3, 4, 5 2s and 2 6s. So we have the square root of, well, these two 2s group up and a 2 comes out. These two 2s group up and a 2 comes out. These two 6s group up and a 6 comes out, and you're left with that 2 underneath. 2 times 2 times 6 is going to be 24. So 24 root 2. Now for extra practice, you could try worksheet 0 and worksheet number 1. Both of these are good. Maybe pick one from each and add it to your notes here. And then you can write down any things to remember. Again, the most important thing here is the simplifying of the roots. We need to be comfortable working with those. So you might want to write down prime factors. Or you might even want to remember your divisibility rules. Divisibility. Rules. So for example, when you divide by 2, it's because it's even. Or you might know, when is it divisible by 3? That's a rule you could look up. The numbers have to add to a sum that's divisible by 3. There's a rule for 5, right? It ends in 0, 5, so on. So you might want to review your divisibility rules for making those prime factor trees. All right, hopefully you enjoyed this video. And as always, thanks for watching.